Hi, welcome all of you. We'll wait for a few more minutes for to join for some more people, and then we'll start the session.
Good evening, sir. Hello.
Yes, I can hear.
Will this, I see that you are recording this. Will it be available for us, the recording?
Yes, I will share update YouTube link maybe. So you can go to YouTube and then watch the prior session. But it will take a few days to get uploaded on YouTube. So
Okay, so,
yeah.
okay, it will be available. I can watch it again, right?
Yes, exactly. So you can refer that later.
Okay, thank you. Thanks.
Yeah. So have you guys finished your first week videos or whichever uploaded on the portal? Am I audible or not?
You're audible, sir.
Yeah, all right. So we'll start today's session. It will be a very short session because the first week was like some kind of informative and it's basic of the basic about the NMR spectroscopy. So I will first introduce myself. I'm Vijay Rane. I'm a Prime Minister Research Fellow in IIT Delhi, and I'm doing my PhD in the organic optoelectronics. So today we are here regarding the course which you have taken on the NPTEL, the 1 and 2 dimensional spectroscopy for the chemist. And in this session, we'll just discuss about some few representative problems. We will not go much detail in this session for the problems. But yeah, if you have any doubts regarding any topic that you are thinking you are confused, not able to understand, you can just discuss here, and that topic we will highlight and discuss in the next session in the more detail. I will provide some problems as well as some more examples, so as you can get clarity over that problem. It is I mean in this is generally for the later case when uh, you are solving actual problems that is structured on the NMR spectroscopies. So maybe proton, carbon, NMR, or we are going for the 2D NMR as well in this course. So yes, this course is uh, taught by Professor N. Suryaprakash. He's from IISc Bangalore, and this course is all about the fundamental concepts of NMR spectroscopy, also the experimental determination of NMR spectra. Then we will also discuss you can see in this course like what are the parameters that affect the NMR spectroscopy, and later also the interpretation of NMR spectra, whatever the raw data that we have collected from the instrument that we will solve in the session, or maybe you can also professor also have solved some taken some problems in maybe third or fourth week sessions, and then we can also go for the heteronuclear NMR spectroscopy, which like including the proton, carbon, and other heteronuclei, maybe the boron NMR as well. So that part all be will be in the later part of this course. So regarding the first week, do you guys have any doubt or anything that you want to? Yeah, you can. Yes. All right. If you don't have doubt, we can directly move for the some problems maybe. So you can stop me in between. At At any point, if you if you have some doubt, we can discuss that one.
Sir, I have one doubt in assignment 10th number question. I am unable to solve that.
Uh, all right, in the assignment, right?
Yes, yes, sir.
So, unfortunately, we cannot directly solve the problems, but we can just I will just see the question, so that we can refer that type of question later. All right, the
Okay.
question is the Larmor frequency. I will just take the question on the screen, right? So, uh, are you able to see the presentation?
Yes, sir.
This is the problem, right?
Yes, yes, sir. I tried, but I am unable to solve.
All right, the question is the Larmor precision frequency of 13C magnetic field of in the magnetic field 16.4 Tesla is 175 megahertz. The magnetic field reduced to 8.2 Tesla. What is the 1H precision frequency? All right, this is like a kind of simple problem that anyway we have already taken this problem. We can solve this problem also. All right,
Okay, sir.
yeah, we can solve this problem or this type of problem. Yeah.
Okay, sir.
Yeah, before we start the problem, also I would like to highlight the exam date is on 3rd November 2024, and also last date for registration without late fees maybe 12th August. But I recommend to register if someone want to register for exam. Please do register for the examination prior before maybe before 10 August, because in the later case, in the last date, the site may have some uh, this is always happen, like site may get crash or some have issues happen with the registration. So it's better to register for the exam beforehand. Yeah, and these are the topics that we have covered in the first week, right? The 1H NMR spectroscopy perspective, NMR of NMR active nuclei, then spin angular momentum, magnetic momentum, interpretation of spin with the magnetic field, then the Lymer precision and energy interaction, and later NMR reduction and sensitivity. So we'll see the one by one problem based on this one. So the first problem is the if oxygen 16 NMR is if oxygen 60 is NMR inactive, which of the following statement is correct? So this will be interactive type session. Hope you will also if you have any uh, if you know the answer, you can tell me in between. So anyone have any option answer here? So they have statement given oxygen 16 is NMR inactive. So what is the reason? So they have given four statements. So the first one was it has odd number of protons and odd number of neutrons. This is the first option. The second option is it has even number of protons and even number of neutrons. Protons and neutrons are even. The third option is it has even number of protons and odd number of neutrons. And the last one, fourth option, it has even number of electrons. So which option is correct one? Does anyone have any answer?
Sir, second option according to me.
Right. So yeah, we can. The second option is it has even number of protons and even number of electrons. This is correct option. Right. Do you know the reason?
Yeah, sir. If we have both of even number, then it is NMR inactive. It's a
Yeah.
paired form.
Right. All are the paired one. Protons as well as all neutrons are paired, so it is NMR inactive one. So whatever the case which has the unpaired protons or neutrons, or we can say the odd number of, that will be the NMR active one. So the option fourth is incorrect. Option third one is also incorrect one. because it mentioned like it has odd number, right? So this should be the active. This is it's not electron doesn't have anything to do with the NMR spectroscopy. So in the NMR we only consider the protons and the neutrons. This you need to take into this you have to keep into the mind, right? So in NMR we already consider about, because NMR is like nuclear magnetic resonance. So we the and whatever entity in the nuclear, that only we are going to consider in this NMR. So the option 2 is the correct option here, right? So anyone have any doubt here?
No, sir.
Yeah. So the next question is here. The 2H1 has the spin is 1, right? The magnetic quantum number is. So they have given the 1H, 2H1 has the spin. Spin is 1. So which option is correct here? So sorry, its magnetic quantum numbers are. So what are the magnetic quantum number if I is equal to 1? So answer, which answer is correct here?
-101.
Right. The -101 option is correct, right? Because you have the spin. Sorry, the what let's say in a nuclei it has. So it is very simple. We can directly put -10 plus 1. It let's say if it has the 1/2, then what will be the answer? What will be the magnetic quantum numbers here in this case? If the I is equal, the spin is equal to, oh, this is for
Uh,
1, right?
half
So
and -half.
right, plus half and
Plus half and -half.
minus half will be the magnetic quantum number for this one. So in this way, you can solve any like whichever the spin given, we can solve this one. The third question is the spin for half nuclei. For the spin 1/2 nuclei, the direction of orientation of spin angular momentum with respect to the magnetic field. So this is the question, and we have the formula. You can keep that noted, the formula. The cos theta is equal to mh upon h under root I in bracket I plus 1, right? So put the value of 1/2 in place of the I, right? So this is value of the I is equal to 1/2. Then if you calculate this all, we will get this, the theta, the right. So this is the angle, that formula you have to keep noted this formula, and then if you calculate this one, the correct option for this one is the 54. So it's just a calculation. You can put the values. Let's say uh, cos theta is equal to here. You can directly neglect this h, right? And you can put m here. In this case will be the 1/2, and if you have the values of the I in bracket I plus 1, so 1/2 plus 1, it will be a 3/2, right? And again here multiply by, here we need to multiply this one by I. Here it will be the 1/2. So overall it will be the 3/2, and which is under root 3/4. So if you calculate this one, though you will get the answer 54.7. So here in this case it is just the formula that we have to take. So this is in the second lecture. It is already given. So I have just took the formula from the second lecture. And yeah, also the axis with respect to z axis, right? So that we have to take here. Here some other example. Let's say if you have the spin is equal to 1. In that case, just I is equal to 1 you have to place, and I just calculated here. So here like you can just put value of I is equal to 1. So it will be, if you calculate this one, it will be 1 upon under root of 1 by 2. So you can just calculate that one. It will be a 45 degree. So you can calculate all for any kind of spin values. You can calculate by using this formula. All right. So the fourth question is the magnetic ratio of the nuclear spin 1H is 26.753 into 10 raised to 7 radian per Tesla per second. This value, we have given 4 options. The option 1 is the increase linearly with magnetic field. The second option is remain constant. Third option is depends on the number of atomic mass, and fourth option is the all the above. So here we have given the fourth option, so we have to pick the whichever the correct option is. So anyone have any idea which option is correct here?
Sir, according to me, increases linearly with the magnetic field.
Anyone other? So here the ratio, we have given the ratio of nuclear spin 1 by 2. We have given, right? So this value remain constant throughout. It doesn't increase with the magnetic field, and also it is not depends on the atomic mass.
Okay, sir.
Yeah, it will be remain constant.
Okay.
The fifth one is the spin quantum number and magnetic quantum number of 19F and 1H identical. That is I is equal to 1 by 2 and M is equal to plus 1 by 2 and minus 1 by 2 and plus 1 by 2. What make them different as far NMR spectroscopy is concerned? So we have given the F19 and 1H. In the both case, I is same for both this one, which is 1 by 2, right? So we have seen the whatever the I values for this fluorine, proton, carbon, and other nuclei. So if you don't remember, I will just pick up that table here. So yeah, this is the table, and here you can see for the proton, carbon, and nitrogen as well as phosphorus, the spin is in the half integer, right? So for proton it is 1 by 2. So in the similar manner for deuterium it is 1, right? Deuterium, that is 2H1. For that one it is I is equal to 1. So in this case you can refer this table for solving the to get to know the spin quantum number for this other nuclei as well. In this case, the fluorine and proton both have the spin quantum number as well as the magnetic quantum number are same. So we have the 4 options. The first option is they have different number of electrons. This is the first option. The second option, their gyrometric ratios are same. Third option is they have different gyrometric ratio. And fourth option is all the above. So what's the correct option here?
Sir,
Anyone?
their gyromagnetic ratio are different means.
Right. Because they here the gyrometric ratios are different for this one. Also, they have different number of electrons. Obviously, it will have the different number of electrons, but it doesn't have anything to do, right? Their gyrometric ratio of same, wrong. This is wrong. They have different gyrometric ratio. This one we have seen in the, I think, fourth lecture, fourth or third lecture maybe. But yeah, in the first week lectures, you have seen all this concept here as well. The seventh question is both magnetic momentum and magnetic field vectors, magnetic momentum mu, magnetic field B0 are vectors. Their interaction energy is given by. So here it is given a cross product. Here it is given by a dot product. You know, right? It is cross product, dot product differences. And the so here uh, the interaction energy. So what is the correct
Sir, dot product.
here, right? The question 7. Yeah. So it is not related by the cross. This one X represent cross product,
Okay, sir.
and dot this dot product. So these are terminology come from, I think, mathematics. So you can refer some mathematics that like what is difference for between the cross product and dot product.
Okay, sir.
Yeah, if it is direction dependent, it is particularly the direction with regard to the direction. So it is the correct option is here. It is dot product of the minus magnetic momentum and the magnetic field. Here the sixth one is the spin of the lithium 7 is 3 by 2. The removal of degeneracy in the magnetic field leads to how many number of energy states? The spin they have given 3 by 2. So degeneracy, you need to calculate degeneracy. So do you know the formula? What is how to calculate the degeneracy?
2i plus 1.
2i plus 1. So put the value of I. So 2 multiplied by 3 by 2 plus 1. So it will be 3 plus 1, 4. So this first option is correct one. So if, you can this very simple problems in this first week. So you may consider this may be boring, but yeah, uh, this is just a starting of this NMR. In the later part, you have actual NMR data. You need to process that one, how to solve that one. So you can go some higher level in the later case. But yeah, let's say if you have the 3 by 2, you can just put the value of I in the simple formula, and you can get the degeneracy in the magnetic field. How many states are possible? How many energy states are possible for such molecule? Let's say if you have I is equal to 1 by 2, just put the value of here. It will be then 2 multiplied by 1 by 2 plus 1. That in that way you can just calculate. So it will be 2, right? Next problem is according to the Boltzmann equation of the population ratio of different energy states compared to the other spectroscopic technique. So what do you think the NMR spectroscopy compared to other technique, whether it is highly sensitive? This is the first option. The second option is it is most insensitive. Third is the population ratios has no relevance to the sensitivity, and fourth one is the population ratio and the sensitivity are inverse to each other. So which option is the correct here?
Sir, it is the most insensitive technique.
Yep, correct. So because we cannot with the NMR we cannot deals with the energy states, right? We can only check the protons, where is the proton, and where is the magnetically active nuclei, how many different type of magnetically active nuclei, that kind of also the electronic effect on that magnetic active nuclei. So let's say if you have some example. So here the bromine is attached, and here is the proton. So what will be effect on the magnetic sorry the value of this one, right? The one in the NMR spectroscopy, that this kind of problem will solve in this once we start the actual proton spectroscopy. But yeah, it doesn't deals with the any energy states, right? So you can only compare uh, this in the advanced techniques. Like do you know any other techniques that actually deals with the population ratios of different energy states and all? So you know the organic molecule, right? let's say this is the organic molecule and which has the different energy states. So this is, let's say, this ground state, it is S0. In the excited state, it will be S1. So these are the different energy states in the organic molecule present. And also in between these are the V0, V1, V2. Here also V0, V1, V2. So these are number of multiple number of energy states are possible. But by NMR spectroscopy, uh, we cannot get any information regarding the population in each energy state. So if we supply any energy to this any compound, so it will go to the excited state. The compound will go to excited state, right? So let's say we have the 10 molecules here, and then we have excited that one. So 7 goes here, 3 remains down. So by NMR spectrum, we cannot tell that it's the how many molecules are excited and how many are in the ground state. So that's the reason it is kind of insensitive technique. But there are other techniques that by which we can get this idea about the ground state and excited state molecules.
Sir, which technique means?
Yeah, so let's say if you take the normal simple UV visible technique, right? So in the UV, what happen? We can get the absorption spectra. So it is right.
Yes, sir.
Yeah. So it will the absorbance, right? So by which we can get, so these many molecules are absorbing. So they in the ground state, they are these much molecules are absorbing. But in the transient absorption spectroscopy, we call it as a TS. We can get the idea about this kind of excited state. So so in the transient absorption, the molecules from here to other excited state, they absorb, right? So in that one, we can get some idea about how many molecules are present in the excited state. So that kind of, we call it as a transient absorption. Also, we have the singlet, right? Singlet. This is S0 and S1, and here triplet. So this kind of idea, the whether there are any molecules are here in the triplet or not, that kind of we can get by using the TRPL. So these are different other technique that like maybe deals with the excited state, but not the NMR spectroscopy.
Okay, sir.
Yeah. So the next question is, when the external magnetic field B0 is changed, the resonance frequency of nuclear spin is. So let's say external magnetic field. So if you have the different NMR instrument like 300 megahertz, 500 megahertz, that kind of NMR instrument we have, right? And does the that we call, so this is like B0. The resonance frequency. Yes. Anyone have any doubt here?
Sir, answer here change linearly.
Yes, it changes linearly. So that's the
Okay.
reason. With the higher megahertz NMR instrument, we get the good quality data, that is good resolution in the NMR spectra. So this part you can get the, with the example you can get a better understanding over this one. So, but I will
Okay,
show
sir.
some example here. Let's say we
Yeah,
have
sir.
the CH2 Br, and here also we have the CH2, right? So for let's consider only focused on this CH2 one. So so it has the one, two, three different type of protons, right? Right. In this one we have this one, and this one. Three different type of protons. So in NMR spectroscopy, we get the proton NMR. We get three different signal. Correct.
Yeah,
Uh,
sir.
and also the splitting constant for this one, the J, the value of J for this one, this CH2 will be the let's say around 6 hertz to 7 hertz, right? Here on the 300 megahertz instrument. 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 300 megahert So if you and we get the spectra like this. But if you do the same NMR, same if you take the data of the same material on the higher megahertz, that is higher magnetic this field one, the higher NMR instrument like 500 megahertz NMR instrument, we get the good resolution here. So initially it might be in the this will be in the 100 megahertz NMR instrument. So then so this will get the triplet, right? Sorry, I just let's change this one. Let's say this is like it will be triplet, not doublet. So with the higher resolution, thus the quality, the resolution, so it will get more and more resolved spectra in the if you go with the higher resolution NMR instrument. So so that's the reason it is increases linearly.
Okay,
Let's
sir.
say
I
this
understand.
500 and this may be a 300, 400. So that's the reason we prefer the 500 or 700 megahertz in NMR instrument than the over 300 megahertz. The last problem is the Larmor precision of the 13C magnetic field is 16 Tesla. So it has given for 13C, which is given 16.4 Tesla, right? At 175 megahertz. And we have given the question, what if, sorry, if it reduced to 8.2 Tesla. So it reduced to how much? 8.2 Tesla. That is almost half, right? What
Yes.
is the precision frequency for the 1H, right? They have given this one for 13C. So we just simply need to multiply these values by 4. Then we'll get it for the proton. So how much it will be? 170 by this one, it will be a 700, right? This is for H1. So this is given for 13C. So we have just back calculation. We did just the back calculation. So we have just calculated for the 1H. Then they have reduced it half here, right? So we need to for calculate for the proton as well then. So we just divide it by 700 by 2. So it will be a 350. So the option C is the correct option here. So do you know why I have multiplied this by 4?
No, sir. I'm not understanding why multiply with 4.
Because it's like for proton, it is the Larmor, sorry, the magnetic field for proton is 16 for 4 Tesla they have given. The natural abundance of the proton is how much? Sorry, hydrogen. 1H is almost 100%, right? Also for 13C is how much? You can just Google it, how much the natural abundance of 13C.
Sir, 13 is natural abundance is very less.
Yeah. So that's why we need a longer time for 13C. So anyway, that's not the anything to do with the this one. But uh,
Sir, I'm not understand why we multiply with 4 that actually.
wait a minute, I will just open the PDF of this one. So there they have given some formula.
Okay, sir.
The exact gyrometric ratio that I need to check that one. But yeah, the gyrometric ratio of the proton is about 4 times higher than the carbon. So that's why I have just multiplied this by 4. So
Okay, sir. So thank you for this.
yeah, yeah. So the gyrometric ratio, you can check that one, how much the exact value. But the let's say the gyrometric ratio for 1H is 4 times higher than 13C. So that's why I just directly correlated that one. So the exact value of the gyrometric ratio, you will get that one. You can found that one anywhere. You can just Google it, then you can get the exact value of the 13C. Sorry, the proton gyrometric ratio, and which is directly related to the this frequency as well. So you can directly by calculation you can just multiply this by 4, then you get the 700 exact for the proton. And here, since they have asked for the 8.2, so which is almost half of this initial value, right? So that's why I just divided it by the uh, 2. Yeah,
Okay, sir. Now I am clearly understand.
yeah. So it has relation with the because of the gyrometric ratio. That's why I have multiplied this by 4.
Okay, sir. Okay,
Yeah.
sir.
So anything else? This is the one problem that someone have asked, right? Initially.
Yes, yes, sir. I means asked.
Oh, all right. So this is the one problem. So anybody have any doubt regarding any problem or the any session that professor has taught in the first week?
No, sir. I have only in doubt in one question that you solved clearly. Means I understand clearly that all things. Thank you for that all.
Yeah. All right. So I think this was since it was the first week. So uh, right now we don't have any doubts maybe because a lot of people I know they haven't started it the watching videos, but I recommend to watch all the video on daily basis. Then and then only you can able to. I mean, in the letter maybe you don't have to require to rush in the letter. I will also upload this. I mean, whatever the problem solving session in the somewhere in YouTube. So you can. I will share the link as well. So if someone missed this one, can later refer that one. So
Okay, sir.
thank you all for joining. So I'm just stop here.
Okay, sir. Thank you, sir, again for
Yeah.
this session.